Okay, I'm gonna get started kind of talking through some of this stuff here. So kind of a lot to write today just because it's kind of just the intro. So there's a lot of vocab words that I just want to make sure we know what they are before we, kind of start talking through those. So the first four here all kind of go together. So experiment, so it's kind of like a science experiment, kind of not. It's more just like something basic like rolling a dice or flipping a coin or like drawing something out of a hat or something like that. It's not like, usually it's not like some sort of science experiment. I think it could still apply to sciencey type experiments, but it's usually not that complex. But it's basically just a situation that's going to have several outcomes, okay? So like the example I've got here, the experiment of like rolling a six-sided die. So that would just be like a normal dice that you're rolling. Now there are going to be some examples in the book that have you roll like other types of dice. So technically there are also other types of dice that have like different numbers of sides. So just be careful there. Normally they'll just tell you what it is. If they don't say, just assume it's just like a normal one, like with six sides. There are these other ones here that they'll sometimes reference to as well, but however many sides it has, just go with that. They have special names, but I don't know what they are. But if they reference that, it's just still a dice. It just has more or less than six sides. But anyway, so experiment is just like whatever action we're doing. So say we just roll a normal dice, okay? The outcome is possible results of that experience, experiments. So like an outcome of rolling a dice could be like rolling a 3 or rolling a 4 or rolling one of those numbers, right? 1 through 6. Sample space then is all of those possible outcomes. So like if you roll just like a normal six-sided dice, our options are 1 through 6, right? Or a flipping coin would be like heads and tails. So sample space is just all the possibilities that you could possibly have. And then event, they're going to reference that sometimes. Event is like a specific part of the experiment. So like say you're rolling a dice and they want you to just roll the evens. Like how many options would you have when you just roll the evens or rolling the odds or something like that? And then those specific events can have outcomes themselves. So that's kind of what those words in general mean. Probability is basically just figuring out the likelihood that something is going to happen. So like the chance that you're going to roll a 6 or flip a coin in its heads or grab something out of a bag and you get whatever. How we do that is, so they're going to reference it with like a P and then something's going to be in these parentheses. P just stands for probability, and whatever is in the parentheses is what we're figuring out the probability of. So here they just do P of E. E is just the event, but it's always the number of possible outcomes of that specific event over the total number of outcomes that are in the sample space. Sometimes books will refer to that as like favorable over total. Favorable is just like the ones we want to happen, or like if that happens we win the game or whatever. But it's always your ones that you want over the total number, okay? And then equally likely, so each outcome has an equal chance of happening. This would be like, so like a coin. So like if I flip a coin, isn't it supposed to be like 50% chance it's heads, 50% chance it's tails? There are some arguments that like flipping a heads is more likely because there's like more metal, or flipping a tails is more likely because there's more metal on the head side and it's heavier and whatever. We're not worrying about that. We're just assuming this is equally likely, or fair is the other word. So if they say it's a fair coin, that means like it's supposed to be like a 50-50 shot. Do you guys know what this coin is? It's huge. It's this big. You might know how much money that is. Does anyone know who's on it? It's a little reflection on it. You might know who that is. That is John F. Kennedy. This is a 50-cent piece. If you've never seen a 50-cent piece before, they're huge. They're bigger than a quarter. They're kind of cool. This is John F. Kennedy's on the 50-cent piece. That's what the other side looks like. It's like the scroll and eagle, or no, eagle of some kind. I don't know. Anyways, coins, flipping coins. Like I said, there's some argument that like one side's heavier than the other or whatever, but don't worry about any of that. Just assume it's like an equal shot each way. Now there are going to be some situations that aren't equally likely. So like say you've got like a bag of marbles and there's like 10 blue ones and 5 red ones. Are the chances of drawing a blue or a red the same if there's more of the blue ones? That wouldn't be. So there are some situations that aren't equally likely, and they'll tell you, or you'll be able to figure it out pretty easily. But anytime we're doing like the dice, they're going to say like it's a fair dice. Technically, there are dice that aren't fair. If you guys ever seen like casino type movies where they like have a little machine that spins the dice to check to see if it's fair, I'm sure you guys have never been to a casino, but they'll put it in a machine to test to see if it's actually like a fair dice, because you can make ones that are like heavy on one side or the other, so it rolls something more often, and obviously that's illegal if you went to a casino. But there are ones that are not fair, which is not legal, so don't worry about that. But we're just assuming all this stuff is fair and there's nothing crazy happening. And then probability, the basics thing there, that's basically just saying all of your numbers for probability are always going to fall between 0 and 1. It could be 0 and it could also be 1. A probability of a 1 is, probability of 1 is there's a 100% chance that it's happening. So like if you flip a coin and you get either heads or tails, are there any other options besides heads or tails? No. So if you flip a heads or a tails and you win, there's a 100% shot you're going to win because there's no other options. The opposite end of that would be like the 0 probability, where like you're never going to win. So like just rolling one dice and getting a 7. Well, if you're just rolling a normal 6-sided dice, are you ever going to get a 7? You would never get a 7, right? So that would have like a 0% or a 0 probability, which you can turn to percents and that kind of thing. But it always falls between the 0 and the 1. And then relative frequency, this is when we actually perform the experiment. So like say you were doing something and you were actually like rolling a dice 10 times and you got results, it would be your true results from that experiment would be a relative frequency. It wouldn't be like what it's supposed to be. Probability is what it's supposed to be. Relative frequency is you actually performing it and seeing what happens or what the results are. Okay? All right, so let's, everybody get a packet. New packet for this chapter. Okay, well, let's look through some of those. Like I said, this probability stuff, it's not too bad. There are some kind of tricky things as we go, but in general, it's not horrible. So first one here, small box contains 30 blue, 30 green, and 25 red paper clips. 2 paper clips are taken from the box and their colors are recorded. List all possible outcomes of this experiment. Okay, so for part A, if we're listing all possible outcomes, that's any combination that we could pull from the bag. Okay, so we got 3 different kinds of paper clips there. Each time we're pulling 2. Okay, so here one possible option, we could pull like 2 blues out, right? So I would just, instead of writing blue each time, I would just say like your blues are B, greens are G, reds are R, something like that. You can write them all the way out, but that's not worth our time writing all those out each time. But one option, we could have like a blue and a blue, right? Another option, usually I try to follow a pattern when I go through these, so what I'm going to do is I'm going to do all of the ones where I pull a blue. So like I could pull a blue and a blue, first option. I could also pull a blue and a green, right? And then I could also pull a blue and a red. And then are there any other combinations with that that you could pull a blue? Like is there anything else we could match with besides blue, green, or red? No, so we're good for blue, so then we just move on from there. So then we go, okay, next option there, let's go with green. So we've already got green and blue, right? That's tackled there. So if we go green and green, that's an option. Or we could go green and red. That's another option. And then I think we've hit all of our greens because we got blue, green, and red. And then what's the only one remaining we haven't paired up yet? The red and the red, yeah. So yeah, those would be all our options there. And then it just wants to know how many outcomes are in that sample space. Well, how many combinations do we have there? Yeah, 6, right? So if there was just 6 possible outcomes we came up with, we would just have 6 outcomes in our sample space. Okay, well, let's jump to that next one there. So that next one is going off of that first example there, like the paperclip example. They just want us to actually figure out some probability stuff with this equally likely business. This gets a little bit tricky, and we'll talk more about this later on. So if we're just finding probability in general, it's like the ones that we want over the total, right? What gets tricky here, though, is when we pull one paperclip out, are we putting that paperclip back in before we're pulling the second one or not? Or are we just pulling 2 out? Are we putting one back in and then re-pulling, or are we just pulling both at the same time? We're pulling both at the same time, okay? So how this works when we figure out probability, it's a little tricky here. So on your first pick, your total number of options, you're going to have 30 blues, 30 greens, and 25 reds, right? So 30, 30, and 25 would be 85. So 85 total paper clips. Now, if I pull one out of that bag, or whatever they're in, Do I still have 85 in that bag to choose from for the second one? I do not, right? I only have 84 that time. So when you do this for your probability, you've got 80, so on your first pick, you've got 85 paper clips in that bag, but once you pull that first one, even if you're pulling them like simultaneously or at the same time, there's always one less in the bag when you do the second one. This is called without replacement when we get to this a little later in the chapter. So on your second pick, you're only going to have 84 in that bag. Does that kind of make sense? So you pull one out, first one, it's 1 out of 85, or whatever number out of 85, next one's only out of 84, okay? So now when we go to figure out our probabilities here, what I'm going to do is I'm going to figure out the probability of each one of those. So I'm going to go like blue, figure out that probability, blue-green, blue-red, and there's other ways to do this. This is just one way with the probability stuff. So what I'm going to do is I'm just going to figure out the probability of each of those, and then they want which outcomes are equally likely, so that means they have the same chance of happening. So I'm going to figure out which ones have the same probability, and that would mean they're equally likely. So here, like I said, for the probability, it gets a little dicey because we are doing it without replacement. So our total's 85, and then for the second pull, it's 84. So when we do this for like blue, when we do our first pull, we had 30 blue, right? And that was out of our bag of 85. So 30 chances to pull a blue out of 85. But then for our second pull, if we've already pulled a blue one, how many blues are left on our second pull? If there was 30 total and we pulled one already, how many's left? 29, right? So now when we do the probability of the other one, it's times in between. It's only 29 out of, and we only have 84 left now. Follow me on that? So because we pulled that blue one out, now we're down to 29 blues left when we do that second pull. And then we're left with 84 in the bag. So then what you would do is you would just multiply those values. So like 30 times 89, I got them on my sheet here, is 870. And then 85 times 84 is 3,570. And I'm just going to leave them like that. You can reduce them down, put them in your calculator, all that. We just have to figure out which numbers are the same, so I'm just going to leave them as those fractions. So then I'm going to work through here and I'm going to do that with the rest of them. So like blue-green, so on my first pull for my blue-green, blue I still had 30 in the bag on the first pull, right? Out of my 85 total in the bag. Now if I pull a green on the second one, does that affect my total green number if I pulled a blue on the first one? It would not, right? Because if I pull the blue, I still have 30 green in there. So 30 for my green, but it will affect my total because I did pull a paper clip out. Follow me so far on why that's 30 and 30? Okay. Like I said, they kind of throw this without replacement into this section, even though we don't do without replacement until later on, so it's kind of messy that they throw this in, but whatever. So then we just multiply that out, so that one would be 900 over, and then our bottom would still be 3,570. And then we just do the same thing with blue-red. So blue again for our first pull, be 30 out of 85. Second pull for our red, if we pull the blue on the first one, does that affect our red number at all? It wouldn't. So our red number is 25 out of 84 total paper clips. And then top number for that one, 30 times 25 is 750 out of 3,570. And then for our greens, so now we're done with the blue stuff. So greens, 30 greens to start with on our first pull out of 85 total paper clips. Then our second one, if we pull green again, what's our second one for green have to be on the top? We pulled one out of the 30. 29, right? Because we've already pulled one out, so there's only 29 left. And we're out of 84 again for total paper clips. So that would be 870 out of 3,570. And then green-red would be 30 for the green again, 85 for the total. And red wouldn't affect our green number at all, right? So our red one would just be as is, so 25 out of 84. 30 times 25, 750 out of that 3,570. And then our last one there would be red. So that'd be 25 out of 85. And then if we pull a red, then we would have one less red for our second pull, so 24 out of 84. And then that one would be 600 out of 3,570. So then what you're looking for there is you're looking for stuff that's equally likely or where they're the same chance of happening. So which of those have the same chance of happening? Or like they're the same probability? Which combinations?
Green, red, and blue, red.
Okay, so if we've got green, red, that's that one, right? That was 750 out of whatever. Blue, red, same thing, right? 750 out of whatever. So that would have an equally likely chance of happening. There's one more here. What's the other one? Yeah, blue, blue, and green, green, right? So that one and that one would also be equally likely. So you could just write that off to the side too. So like blue, blue, and green, green are equally likely. And again, that just means they have the same chance of happening, as well as blue, red, and green, red are equally likely. And again, that's because they have that same probability that that happens. Now, like I said, there's other ways to figure that out too, but since we're working on probability, I figured we just talk through it that way. Okay, now there's actually one more here. I don't know why I didn't have it on the sheet. There's another one, but there is one on the next page too we'll get to. You guys okay if I flip? Okay. All right. So now this one here, we got lots of options for this one. So assume that the births of boys and girls are equally likely. They don't, I think there's like a typo here that's in the book and that's not on the sheet here. We should know that it's a family of 4 kids. So for this one, when they're figuring out outcomes in sample space, right in there, it's a family of 4 kids. They don't say that in the directions there. I think that's just a typo. So here we're assuming that if a boy is born versus if a girl is born, there's an equally likely chance of that happening. Obviously, genetics plays a role into that too, but again, we're not worrying about those types of things when we're doing this. We're just assuming it's an equal shot of having a boy versus a girl. So for the first one, how many outcomes are there in the sample space? What I typically do on one like this, if there's like a shit ton of options, is I'll actually make a tree diagram. It's probably not the most efficient way of doing it, but it kind of gives you a visual that you're going to need to kind of answer some of the questions in a little bit here. So I like to make a tree diagram. Do you guys know what I'm talking about, tree diagram? You'll know when I start doing it here. So like for the first one, so there's 4 kids in this family. So like first kid, second kid, third kid, and fourth kid. When the first kid's born, options boy, girl, right? So we could have boy, we could have girl as our options, right? Now, after the first kid is born, does whatever gender or whatever the first kid is, does that have an effect on the second kid? It does not, right? So off of the boy, we could either have a boy or a girl, right? Same on the girl. Coming off of that, first kid's a girl, second kid could be a boy or a girl. And then you'll just keep working that out there. So like on the third kid then, the boy would have the option boy, girl. Same thing coming off the girl. Boy, girl. Same thing all the way down there. And then same thing with the fourth kid. So coming off of each of those ones you've got then, you'll also go boy, girl. So again, I like to do this when there's like quite a few options, and then they ask me questions about those specific options. If I just need to figure out the number of options, that's not too bad, but then when they start asking specifics, it's nice to have a visual. So tree diagram's one route you can go. So then once you get that all kind of laid out there, when it says like how many outcomes are in that sample space, each one of these kind of branches off here represents a different outcome. So like this top one here would be like boy, 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 boy. So if you had all 4 boys, that would be that first branch. Now the next one here would be boy, 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 girl, right? And then you just kind of keep working your way through there where each of those would be a combination, but you're not writing every single combination out. So to count up how many total combinations there are, you just count how many are in this last column here. And if we kept doubling and doubling and doubling, so like if we went like 2, 2, 2, and 2 there, that would get us out to 16 possible combinations. And again, you could just count up those different numbers there, and all of those different combinations would be like the sample space options. So then when it says find the probability that a family of 4 has 1 girl and 3 boys, what you want to do there is you want to look through your options and figure out how many of those options have 1 girl and 3 boys, okay? And that's why I kind of like to have a visual. So what you can do here, so if we've got to have 3 boys, we got boy, 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 but then the last one's got to be a girl, right? So wouldn't this combination here be one of our options? It would be, right? So I'm going to highlight those or circle them so I know which ones I picked. So like that's an option because I went boy, 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 girl, okay? Now if I'm looking for that again where I've got 3 boys, why if I go boy, boy, this one's a girl, but if I jump back to boy, wouldn't that be another option if I go 3 boys and 1 girl? And then nothing there. This one should be good because we go boy, girl, but then we end with 2 boys. So that'd be good. And then girl, I don't think we got any more there. So then girl, I think the only option for this last group then would be because it's starting with a girl, so the only one that would work here is when the other 3 are boys. So that would be an option, but past that I don't think any of those will work because they would all have combinations of girls mixed throughout. So I think it's just those 4. So if we're doing probability, it's the ones that we want over the total. So here the ones that we're looking at would be the ones that we picked there. So 4, this is part B, 4 out of the 16 total options that we had for our sample space. And then we know that that could reduce down if we pull a 4 out of each of those. You could also take it down to 1/4. I don't care which route you go there. Sometimes people also do it as like 25% or 0.25. Any of those would be fine for probability. Okay? Alright. Like I said, not too bad. Okay, so got that book page there for tomorrow, and then tomorrow we'll go on to next section 6, 2 stuff.